So in addressing the innovations of the Industrial Revolution, it's often divided up into two phases. The first phase of the Industrial Revolution includes innovation not only within transportation, but also communication. Now, in looking at, the so-called age of steam and iron, it was launched in 1765 when James Watt invented the world's first steam engine, at least the world's first workable steam engine. Now, he built upon his earlier experiments with steam pumps, and his new machine was powered by coal, which it was found in abundance in Great Britain. Coal production will increase tenfold in England between 1750 and 1850. All right, so the steam engine kicks it off. By 1850, every nation that either was or wanted to become industrialized was building railroads. Great Britain's railroad growth actually leveled off at about 20,000 miles by the 1870s, while Germany, France, Canada, and Russia ended up building more lines than Britain. Now, Japan gets in the game by starting to build in 1870s, and they imported US and British engineers to begin the process. Once the Japanese had trained engineers of their own by the 1880s, they sent all of the foreign engineers home. Now, the rails reached every single province and city in Japan by the 20th century. The United States by far had the most rail lines. So by the end of the Civil War, there were 35,000 miles of track. And by World War I, there was 400,000 miles of track, which was longer than the next 7 longest networks combined. Now, developing nations also had railroads if they could be of benefit to a nation or business. Regions with abundant raw materials or agricultural products, like South Africa and Mexico and Argentina, or densely populated areas like Egypt, saw new railways. The fourth largest rail network in the world was built in India by the British because they wanted to reinforce their presence and establish trade in their largest colony. Until the Panama Canal was constructed, a railroad carried freight from the Atlantic to the Pacific across the isthmus. And most railroads in these developing nations were built with European or American engineers using imported parts. The only exception was Japan, who, they got their foreign help and then began to build railroads using parts manufactured in Japan. Now, due to the presence of the railroads, many cities doubled in size, and these cities need to accommodate the tracks, the warehouses, the repair shops, and other aspects of the industry. Railroads also will require bridges, tunnels, and embankments in the countryside. Vast quantities of timber are used for the ties and bridges, and these would consume entire forests. So new land now opens up to agriculture, mining, or additional exploitation of natural resources. So the steam engine first kicks off railroad growth. Eventually, it leads to new steamships. And the first ones were developed by the 1830s, but they were too expensive for anyone but the wealthy. By the middle of the century, iron and then steel replaced wood as the material used in hull construction, and propellers will replace paddle wheels. The engines become much more powerful and fuel efficient. The average size of a freighter jumps from 200 tons in 1850 to 7,500 tons in 1900. Coaling stations and ports that were able to handle large ships are built around the world. And the Suez Canal, built in 1869, shortened the distance between Europe and Asia, and it helps trigger the switch from sail power to steam power. Now, when you see regular shipping lines, the steamships were costly to build, so they had to be utilized efficiently. The concept of the shipping line developed, and this meant that a company offered fast, punctual, and reliable service based on a fixed schedule. So people, mail, and perishable freight will travel along these regular routes. Many ships actually went from one port to another under orders from their company headquarters or amongst places in Europe and North America. Now, when we look at communication, a new revolutionary method of communication were marine telegraph cables. These were laid on the Atlantic floor in 1866. They connected to India by 1870, and most areas of the developing world had them by the mid-1880s. And by the turn of the century, nearly every country and inhabited island was connected by these cables. Cables were critical tools of modern shipping and business, and the press referred to the annihilation of time and space to describe this new phenomenon. So in the first phase, we have steam power, we have telegraph cables and railroads. Steel and chemicals are the tools that kicked off what are often called the second industrial revolution. Now, steel itself is a hard and elastic form of iron. Until the 1800s, it could only be made by highly skilled blacksmiths in small quantities, and it was very expensive. So it was reserved for items like swords, knives, and axes. In the 1850s, a Kentucky airmaster discovered that air forced through molten pig iron that was used with powerful pumps turned iron into steel without any extra fuel. And in 1856, Henry Bessemer discovered how to improve on this method and produce steel at 1/10 the cost. This is the Bessemer process. And further discoveries permitted the production of steel from scrap iron. Production will rise from 500,000 tons in 1870 to 28 million tons annually in 1900. Now, the U.S. takes the lead, and annually they produce 10 million tons, followed by Germany at 8 and Great Britain at nearly 5 million. There was enough steel to construct bridges, rails, ships, and tin cans that could be thrown away when used only once. Now, chemicals followed the same process as they were traditionally produced by trial and error. By the early 1800s, sulfuric acid and chlorine bleach were produced in large quantities. The first synthetic dye was created in 1856 from coal tar, and so that's why you see it was a purple dye. And German scientists created additional dyes by the end of the century. You see the word explosives. In 1866, Swedish scientist Alfred Nobel turned nitroglycerin into more stable dynamite. These new explosives were crucial in the construction of railroads and canals, as well as in mining operations. And they enabled armies and navies to become armed with more accurate cannon and rifles. Now we see fusion of science and technology with Germany in parentheses. The chemical component of the Industrial Revolution provided one of the first fields where science and technology interacted on a daily basis. This provided Germany with a clear advantage, since they had the most engineering schools and scientific institutions. The German government funded research and encouraged cooperation between universities and industries. So by the end of the 1800s, Germany was the leading producer of dyes, drugs, ammonia, and nitrates for explosives, positioning them as a military power. Now, entire regions will be affected by these industries. Mills consumed massive quantities of resources and took up as much space as did small towns. Steam engines polluted the air with thick smoke, and dyes and other chemicals left toxic wastes that were normally just dumped in nearby rivers. Unchecked industry harmed the environment, and it'll damage the health of inhabitants. So steel and chemicals are the first components of this second industrial revolution. Electricity is the other one. And all things considered, electricity could maybe be considered the biggest game changer. It was initially so expensive that it was only used for electroplating and for telegraphs. So we see the pattern that most of these innovations were very expensive and had limited use. But in the early 1800s, it was discovered that the motion of a copper wire through a magnetic field would produce an electric current in the wire. Inventors in the 1870s used this knowledge to create generators that turned mechanical energy into electricity. It was much more flexible and easier to use than water power or the steam engine. So that's where we see it might be considered better than water or steam. Now, lamps began to light up public squares, theaters, and stores. In the late 1870s, Thomas Edison helped develop an incandescent lamp that was useful in lighting small rooms. Several years later, he created the first electrical distribution network in New York City. By the turn of the century, electric lighting replaced the dim and smelly gas lamps in the major cities of Europe and North America. Now, before long, electricity was applied to additional uses. Streetcars and eventually subways helped reduce traffic jams that clogged streets in Europe and North America. Electric motors increased productivity and worker safety, and engineers even used water power to create electricity. Hydroelectric plants were built, and the Niagara Falls plant produced 11,000 horsepower when it opened in 1895. The first professor of electrical engineering taught at the Imperial College of Engineering in Japan, and his students went on to found major corporations and research institutes. So this industrial process, certainly has been ongoing. It's often said that the Industrial Revolution was the second large change, the second shift in human history. It began with the Neolithic Revolution, or the shift from hunter-gatherer societies to settled agriculture thousands of years ago. So declaring the Industrial Revolution and its effects to be the second great shift is certainly no light matter.